So, welcome back to our next talk by Jose Bastidas on the polytope algebra of the generalized perimeter.
Thanks, Roman, and thanks to organizers for making this space possible to share all of our recent research, and especially for giving me the opportunity to talk here. So let me dive right away with the definition of the polytope algebra as defined by Macmillan, because I feel that maybe this is not something that is super well known as it maybe deserves to be. So we're going to start with an abelian group that is generated by classes of polytopes that I'm denoting with this bracket. So we have classes for every polytope in RT. And these classes satisfy two relations. The first one is a translation invariance relation. So I'm considering polytopes up to translation. And the second is this relation right here that says that whenever the union of two polytopes P and Q is convex, again, it's a polytope, we have this relation. The class of P plus the class of Q equals the class of the union plus the class of the intersection. And here in this example, we have an instance of this relation if we overlap these two parallelograms on this marked point right here. So if we put these 2 points together, the union of these two parallelograms is this trapezoid, and the intersection is precisely this simple X right here. So this is one instance of this relation. And we're going to impose a product structure as well on this group. And the product is given by the Minkowski sum of polytopes. So on these generators, we define the product of two classes of polytopes with the class of the Minkowski sum. And here we have an example of such a product. So if we multiply the simplex by this segment, the result is the class of this Minkowski sum. And geometrically, to see how this Minkowski sum looks like, we're just taking, for instance, the segment, the second polytope, and traversing the simplex with that line segment. And the resulting collection of all the points that we traverse is precisely this trapezoid right here on the right. We already see with these definitions that there is a unit for this ring so far, and the unit is the class of any point, right? All of the points are the same because they're equal up to translation. And we also see nice identities like this one, for instance. So if we take any non-negative integer n and we take the class of a polytope and raise it to the nth power, the resulting class will be the class of the nth dilation of that polytope, so just multiplying every vector by a factor of n. Okay, so Macmillan introduced this back in '89, and he showed that the resulting ring is a graded ring. This is not easy at all, but he nonetheless managed to prove so, and it's actually finitely graded, right? It goes up to degree T, where it is the dimension of the ambient space. And if we take a k-dimensional polytope P and we take the class of the polytope and break it out into its homogeneous components in the algebra, it's going to look something like this. So in degree 0, we always have a 1, and then we have some non-zero pieces up to degree k, where k is the dimension of the polytope. So here I have a couple of examples of such a computation. I'm not going to say how I obtain these things right here. It's not super easy, but also not super complicated. But rather I want to focus on some of the nice properties that we can see if we manipulate expressions like this. So what happens, for instance, if we compute the first graded component of the Minkowski sum of two polytopes P and Q? As we said, this was the product in this algebra, in this ring. And if we expand, we see that in degree 1, taking the Minkowski sum of two polytopes corresponds to just taking the sum of the degree 1 parts of those polytopes. And similarly, if we take a dilation by let's say a non-negative integer n of a polytope, in degree 1, that just corresponds to multiplying by n. Okay, I'm not saying anything about what happens in higher degree, but at least in degree 1, Minkowski sums turn into just sums, and dilations by non-negative integers becomes multiplying by that non-negative integer. And this is in fact true not only for integers, but for any real number. And we can say this by saying that weighted Minkowski sums of polytopes, or Minkowski sums where we are also allowed to dilate by non-negative factors our polytopes, translate into linear combinations in this first graded piece of this algebra. And here I'm just saying the same thing in formulas. And if you notice, because these lambdas can be any real number, we're giving this first graded component at least the structure of a real vector space. And actually, this can be improved, and we can translate this structure, or we can impose this structure on the other graded components. So this is actually an algebra, an R-graded algebra. For those that are experts in this and know about this algebra, you know that the degree 0 piece is not actually a vector space, but we can tensor with R and make it so. And this is something that Macmillan already did in the subsequent papers about this. But now we're not going to consider the full polytope algebra, so this algebra that we have defined here. And we're going to consider something smaller, something that lives inside of this. So we're going to start by picking a sonotube. A sonotube is just a Minkowski sum of segments. So we're going to have, in this example, have these 4 segments, and the Minkowski sum is this sonotube right here. And we're going to consider the subalgebra generated by the classes of all deformations of this sonotube. So deformations is something that we can define for any polytope. But in the case of sonotubes, there's a very nice description of what a deformation is. It's just a polytope whose edge segments, the edge directions of the polytope are the same as the edge directions of these summands that we have here. So for example, this one right here is a deformation of C because this edge is parallel to this one, and this edge is parallel to this summand, and so on. So these are classes of deformations of this sonotube. I want to start by observing that actually this subring that we're considering is not dependent on precisely which segments we pick, right? It just depends on what the directions of the segments are. So it only depends on the underlying hyperplane arrangement. So to every sonotube, we associate a hyperplane arrangement that consists of the hyperplanes that are perpendicular to the line segments defining our sonotube. And this subalgebra is only dependent on that arrangement. So we could directly associate it to the arrangement instead of thinking of what sonotube we start with. A second observation, or maybe fact, is that this new algebra that we're considering is finite dimensional, unlike the original full polytope algebra, which in other than degree 0 and degree t, all the other degrees are infinite dimensional as vector spaces. And moreover, Macmillan showed that if our sonotube is simple, the sonotube that we start with is simple, or equivalently the hyperplane arrangement is simplicial, then the dimensions of these graded pieces are just the H numbers of the sonotube. So just combinatorial information to determine the dimensions of these spaces. But now, if you recall from the talk of Stuart on Monday, there is another algebraic structure that we can associate to a hyperplane arrangement, another algebra. And this is the algebra of phases of the arrangement. So Stuart made a great introduction to this algebra, but I'm just going to quickly review what the underlying monoid is. So we're going to consider the collection of all the phases of the arrangement, which are, in this case, for example, the 8 regions, the 8 rays, and the central phase, this origin right here. And the product of 2 phases, say F and C, is the first phase that we encounter if we walk from an interior point in F to an interior point in C. So if we start walking in this direction, as soon as we move a small positive distance, we will be in the interior of this 2-dimensional phase, and this is the product F times C. Okay, so this defines a monoid on the collection of phases, and the Dietz algebra is just the monoid algebra of this monoid. So we're allowed to take linear combinations of phases now. And the starting point of this new work is that actually the sonotube algebra, so the polytope algebra relative to this sonotube, has also the structure of a module over this algebra of phases of the arrangement. Okay, so to define a module structure, I'm going to take one of the generators of the algebra, so the formation of C, and I'm going to say what happens when I multiply by a phase of the arrangement. And the definition of this action is very simple. We're just going to take the phase of this polytope that is maximized in the direction of that phase. So what does this mean? It means we can take any direction or any vector that is in the interior of the phase of the arrangement that we're using. When we look at the phase of Q that is maximum in that direction. The fact that this is well defined is precisely because Q is a deformation of the sonotube C, and the phases of the arrangement form the normal fan of the sonotube C. So this is well defined, and then we have to check that this actually preserves the relations that define the polytope algebra, but this is not very difficult to do. And moreover, what we have is that not only the polytope algebra of the sonotube is a module, but in fact, every graded piece is a module, right? So this decomposition that we have into graded pieces, it's actually the composition into modules as well. So now we have this final information, and we can keep asking, can we say something more about each of these graded pieces as modules over the phase algebra of the arrangement? So let me introduce these little technical details. So remember that for any hyperplane arrangement, we have a lattice associated to it. That's the lattice of intersections, or the lattice of flats of the arrangement. A flat of the arrangement is any arbitrary intersection of some of the hyperplanes of the arrangement. So for example, here we have each hyperplane by itself, that's a flat. We're just taking the intersection of one hyperplane. If we intersect any two hyperplanes in this particular example, we already obtain the origin, so that's a flat as well. And if we intersect no hyperplanes at all, we have the ambient space, in this case R2. That's also always a flat. And in this case, I'm ordering them by inclusion. Sometimes I order it by reverse inclusion. It's not going to be super important for now. I'm just using this notation. And Saliola constructed this family of orthogonal, of a complete system of orthogonal idempotents for the t-algebra of the arrangement that are indexed by the flats of the arrangement. So I'm not going to explain what a complete system of orthogonal idempotents is, but rather I'm going to say that the existence of such elements, or given a collection of such elements, we can get a decomposition of any module over the t-algebra of this form. So we're decomposing any module. In this case, we're going to take these graded components and decompose them into certain subspaces indexed by the flats of the arrangement. Okay, I want to emphasize that these subspaces are not necessarily submodules; they're just subspaces. And we have formulas. So actually, in later work of Ayala and Mahajan on these same idempotents, they give formulas to compute the dimensions of these subspaces, and we can utilize these formulas in this particular case. And well, with some small technical details, we can find formulas for the dimensions of these subspaces. These dimensions have algebraic meaning, so they are counting certain multiplicitives or of certain simple modules, and not a direct sum decomposition of the module, but something similar that we can do. But rather of thinking of this algebraic interpretation of these numbers, let's just think of them in combinatorial terms. So at least in the simplicial case, because we know by results of Macmillan that the dimensions of these spaces are the H numbers of the sonotope, what we have now is a refinement of those H numbers. And if the H numbers themselves are interesting, maybe this refinement will be interesting as well. So we're going to take this very combinatorial approach to these numbers. Okay, let's do this in a very interesting case, I think for everyone, the case of generalized permutahedron. So in this case, our arrangement will be the braid arrangement that consists of hyperplanes xi equals xj for I different than j. The corresponding sonotope will be the permutahedron, so the polytope whose vertices are of the form any permutation of the entries 1 through d. It is not obvious from this presentation, but this is a sonotope, so we can also write it as a Minkowski sum of segments perpendicular to the hyperplanes of the braid arrangement. And the braid arrangement is not any particular arrangement. It has a lot of importance because it's one of these very special reflection arrangements. And the corresponding group, the reflection group of the braid associated to the braid arrangement, is the symmetric group. So things that we are very familiar with. Now, the H numbers for this polytope, for this sonotope, the permutahedron, are very well known. And in fact, in work of Björner and Brenty, they computed the H numbers, not only for this particular permutahedron, but for the permutahedron associated to any Coxeter, finite Coxeter group. So if W is a finite Coxeter group, then the H numbers of the associated W permutahedron are just the W Eulerian numbers of that Coxeter group. I think this is something that Sarah mentioned yesterday. So these W Eulerian numbers are defined in terms of descents in the corresponding Coxeter group. But for this particular example, let me take a different approach, an equivalent definition of the classical Eulerian numbers, so the Eulerian numbers for the symmetric group, which is the following. The Eulerian number ADR is counting the number of permutations on the elements that have exactly R exceedances. Usually it's defined with the number of permutations that have exactly R descents, but this is an equivalent definition, the number of permutations that have exactly R exceedances. And remember that an exceedance of a permutation is a value I such that when I apply the permutation to I get something strictly bigger. So let's see how these numbers look in the case of D equals 3. If we want to have exactly 0 exceedances, the only possible permutation that has that is the identity permutation. So there is only one. So this number is 1, A30 is 1. If we want to have exactly 1 exceedance, well, these are the 4 permutations of 3 elements that have exactly 1 exceedance. I'm writing them in cycle notation, and the bold element is the exceedance. This 4 over here should be a 3, sorry. And we see that there are 4 such permutations. And if we want to have a permutation that has 2 exceedances, there's only 1 possibility. And if you remember these numbers 1 for 1, they came up already yesterday in John's talk. These are the Eulerian numbers for this particular case for b equals 3. Okay. The result here is a computation for the formulas for the dimensions of these subspaces. So for any flat x, remember that these things were indexed by degree and a flat. So for any flat and any degree between 0 and d minus 1 because the polytope is d minus 1 dimensional, the dimension of that corresponding subspace has a combinatorial interpretation, and that interpretation is the number of permutations that have exactly r exciences. So we are refining these Eulerian numbers, and the refinement is given by these conditions. So we're going to associate this permutation to the flat x if, when we look at the action of the permutation on the ambient space on Rd, the collection of points that are fixed by this action is precisely the flat x. Okay. So just to give you an example, what happens if we look at this permutation right here, this cycle? If a point in Rd is fixed by the action of this cycle, then x1 has to be equal to x3, and x3 has to be equal to x2. So all the coordinates have to be the same. So that happens precisely in the intersection of these 3 hyperplanes. So the flat associated to this permutation is just the minimum flat intersection of all hyperplanes. And for instance, the flat associated to this transposition is precisely the hyperplane x1 equals x2. Okay. I'll make a very brief parenthesis and mention that this algebraic structure, so this modular structure that we're imposing on generalized permutahedra, can be extended to all dimensions, because we can do the same in each dimension. So in Rd for every possible d. And this is very related with the Hopf monad of generalized permutahedra defined by Aguirre and Ardile. And something similar to this construction for the particular case of generalized permutahedra was also done by Ardile and Sanchez around the same time. But I just want to mention this because they were working on something very similar, but I won't approach this Hopf monad point of view today that much. It was just a parenthesis. Okay, so this is a very interesting refinement of the Eulerian numbers in the classical case for type A. Now let's see what happens in type B. There's something very similar that we can do. In this case, the hyperplane arrangement associated to the Coxeter group of type B has hyperplanes xi equals xj, xi equals negative xj, and the coordinate hyperplanes. The associated Coxeter group is called the hyperoctahedral group, or the group of signed permutations. And the permutahedron here is the type B permutahedron. So this is just a sonotype of this arrangement. I'm not going to give all the definitions here, but there's a very similarly looking theorem in type B. So again, the dimensions of these spaces that are, again, indexed by degree and a flat of the arrangement are counting certain permutations, certain signed permutations with respect to these parameters. And if you're familiar with statistics on signed permutations, then you'll know that there are many definitions of exceedances in type B. And if I put a different, so I have to pick the right definition of exceedance. Not all of them are going to fit this theorem correctly. The one that works is one that it's related to flag exceedances, if you have heard that, okay? But I'm not going to give the full definitions. Rather, I'm going to see how to use these combinatorial information, these numbers that we have computed, to say something more interesting, okay? Okay, so let me move on, and let me go back again to the general case of any sonotype. And remember that on the second slide, we said that weighted Minkowski sums of polytopes in general, if we just look at the first graded component, they translate it into linear combinations of the classes of the polytopes, right? And now let's look at what happens if we fix a sonotype and we just look at the formations of that sonotype. Then we have this space, the first graded piece. This is a finite dimensional space. Let's say this square right here. And inside of that vector space, we have a very special cone. It's the formation cone of this sonotype. So this is just the cone formed by all the classes of polytopes, of the formations of the sonotype C. And this is actually a cone because of the properties that we discussed before, right? If I have, for instance, the class of P and the class of Q, again, just the first graded component of that, and I take the sum of these two classes, that will correspond to the class of their Minkowski sum, another deformation of the same sonotype. So all of this is closed under sums and there are non-negative dilation. So this is an honest cone in this vector space. But you can also have some linear combinations that don't use only positive coefficients. We can have linear combinations that have negative coefficients and still land inside of this cone. So that means at this point, even though I'm writing it as a difference of these two classes, represents an honest deformation of C. So whatever this deformation is, satisfies that deformation Minkowski sum with R equals the Minkowski sum of P and Q. So we can say that this polytope is the signed Minkowski sum P plus Q minus R. It makes sense. Not all Minkowski difference makes sense, but this one does. And of course, we have things that are outside of this cone. So these formal linear combinations, they do not represent an honest deformation of C, but they are sometimes called virtual polytopes or virtual deformations of C, if you want. Okay, so this is very general. And whenever we have something like this, whenever we are trying to understand this cone, this deformation cone, and I'm using this little t here to emphasize that everything is modulo translation. So this is not the actual deformation cone, it's the deformation cone modulo translations. Something that people are interested in doing is, well, understanding the phase structure of this cone, but this is very difficult. Usually these cones have a very, very large number of rays if we compare them to the dimension where they live in. So it's kind of hard to describe all of the rays of this cone. But something that we can at least try to do is to find a basis for this space. So remember, this is just a vector space that is formed by some cones of this arrangement. So sorry, some rays of this cone, okay? So that's something that's feasible to do. And the module structure that we introduced before allows us to tell us something about which choices are feasible. So this proposition right here is telling us that if we're going to do so, if we're going to pick a certain collection of rays of the cone that form a basis for this space, we are going to need at least this many rays that represent full dimensional polytopes or maximal dimension polytopes, polytopes of the same dimension as C. And the reason is very simple. So there's a technical lemma behind this, but the idea is that if I have something that is not full dimensional, when I project with this idempotent, this is the idempotent associated to the minimum flat. When I project with that, I get 0. So this projection annihilates anything that is not of maximal dimension. That's basically the reason behind. So yes, this is telling us, okay, this number has actually another important meaning. They're going to give us a lower bound on the number of full dimensional polytopes that I need to get a basis of polytopes for this space. Let's see what this is telling us in type A, which is a very well-known case. In this case, this number is just 1. And okay, that's very nice because let's see what happens here in an example in R3. So if we take a slice of this deformation cone, in this case, the deformation cone modulo translations is of dimension 4. So we're taking a slice of dimension 3. And I think this picture came up this morning in Dorian's talk as well. If we look at this slice of the cone, we see that if we're going to get a basis of this, we are going to have to use at least either this simplex or the reverse simplex, right? I cannot get away without choosing at least one of these two. And actually, I can get away with picking exactly one of them, right? I can, this is a known result of Postnikov and then extended by Ardila, Benedetti, and Docker, that I can choose the standard simplex and all of its phases, which are of course of dimension strictly lower than the dimension of the simplex. And those will form a basis for the space of deformation, of virtual deformations of the permutahedron. And this is basically the statement that I have written here. I want to point out that their proof is constructive. So they don't only say, okay, these form a basis, but also they say, if you have this generalized permutahedron given by these inequalities, in this way you can construct the coefficients to get the signed Minkowski sum. And because of time, let me go quickly over here. We can ask the same question for type B. And in fact, Ardila, Castillo, Ure, and Postnikov asked this in FPSAC 2019. Is there an analogous result in type B? And the result that I showed before is going to imply that in type B, we're going to need at least 2 to the d-1 full dimensional polytopes. This question was partially answered by Padrol, Pilo, and Ritter, again, earlier today, with the constructions of shard polytopes, which they prove they form a basis for this space. I think they only conjecture that they are rays, but they form a basis nonetheless. But the array in R3, we see that they have 14 full dimensional polytopes. And I'm not going to explain the construction, but it is possible to slice the cross polytope in a, well, with a coordinate hyperplanar, with the coordinate hyperplanes, and then picking simplices in a clever way. to construct two different bases of rays, one that has exactly these manifold dimensional polytopes, and one that it's maybe nicer because it's more symmetric. And again, I want to emphasize that the construction or the proof at the end is again constructive because we can say, given any bisubmodular function that defines a type B generalized pentaedron, how we get the coefficients that gives us a sine Minkowski representation of that type B generalized pentaedron. With that, I want to finish. Thank you.
All right, thank you very much. Are there any questions? Not really a question from Manau. He just confirms that the sharp polytopes are indeed rays of the submodular cone.
That's very nice.
Can you make a remark on this Postnikov theorem about what is the weighted Minkowski sum?
Yes, so I don't remember exactly the formula, but the formula is very, so over here, it's very simple. So, given
what is side-net sum? So it is what difference of Minkowski polytope?
Exactly. So it's something like this. Over here, we can say that this point represents a polytope, and we can say we can give a sine Minkowski expression for this polytope as P plus Q minus R.
But then I can give you a remark that such a theorem was proven in 2000 with me and Danilov.
Okay, I didn't know that. Thanks. Yeah.
Published.
I have to look at the references.
Yes, it's Minkowski sum and difference somehow. Yeah, so I will share in the chat.
Okay, thank you. Perfect.
Okay. So if there are no other questions, then let's thank you again. And we restart in 3 minutes with the last talk of the afternoon session.